Hi, welcome back. I'm glad you decided to join us for a couple of more examples on how we can use double integrals to find areas. Now, in both examples down here, these are both polar graphs. So I'm going to choose to use my polar method to find the area. Last year in single variable calculus, we learned to find the area of a polar by using this formula right here. And we have a video on this, and we proved this last year. If you forgot how to prove it, I have another video on that. Please go take a look back at that. But to solve a problem like this using polar functions, we have to determine our area. Remember, we talked about this. This is our lesson. The change in area is r dr d theta. And we showed how we got this a few times. And the first thing we notice is we need to get the change in radius. So I have to get my change in radius. Well, how do we do that? Well, we start with what the minimum radius is going to be, which is going to be 0. And as we move along the surface right here, my radius, r, is changing. But the radius is always defined as this function. So the radius is always r equals 2 sine theta. So the maximum radius will always be 2 sine theta, depending on whatever theta is going to be. So there's my minimum radius, and there's my maximum radius. Well, after we get that, then we have to get our change in theta, delta theta. Well, be careful. You want to be really careful with this one. As we move around, right? As we move around, one of our rules was this only goes from 0 to pi to make one circle. If you go 0 to 2 pi, you're going to make 2 circles. This is from pre-cal. It's a little bit of a pre-cal review for you. So if I want to find my area, my integral is going to be the region area of the base, dA. But for polars, I guess we already did that. For polars, dA is r dr d theta. So I can go ahead and find my area, r dr d theta. And my change in radius goes from 0 to 2 sine theta, and my change in theta goes from 0 to pi. And that would be our area here. Now what's really neat about this is, watch this. If I integrate just with respect to r, we're going to get r squared over 2 from 0 to 2 sine theta. And if we square that, we're going to get 2 sine squared theta. Whoops, sorry. I got to square that. That should be a 4 sine squared theta over 2. And we're going to integrate that with d theta from 0 to pi. And if you notice, 1/2 r squared, 1/2 r squared. So we actually do get the same exact formula if we were to start integrating. Alright, so let's take a look at number 21. This is a butt graph. You might recognize it from pre-cal or one of our cardioids. So if I want to solve this one, same idea, with polars, I need the change in radius and the change in theta. Well, the change in radius, starting at the pole, the minimum is going to be a 0. And the maximum is going to be is the surface itself, is the shape itself, which is this 2 plus 2 sine of theta. Now the angle for our cardioids goes from 0 to 2 pi. So I can write my area, my double integral, 0 to 2 pi, 0 to 2 plus 2 sine of theta, and this is going to become r dr d theta. Don't forget the r. That's the one thing people forget. Remember, in rectangular, the area is dy dx. But in polar, the area is r dr d theta. Remember, where this really comes from is the this little bitty arc length, S, times times the radius. Remember we talked about this arc length right here, S, remember is times theta, excuse me. S times theta. There we go. Sorry, let me scratch that out. Oops, sorry. Let me go scratch that out. So remember, this RdR is our theta, so this is really the arc length times the change in radius. So if I go like two little pieces right here, this arc length times that little change in radius, and it makes kind of a little bit of a rectangle, where S is my R times the d theta times dr. That's my arc length, that radius times that little tiny change as we go to 0. We do have a video on this, so please take a look at that if you need to. Okay, I hope you enjoyed the video. I'll see you later. Bye-bye.